It's a great pleasure to be here and actually to talk about Thurston's work. So, the plan for today is that I want to discuss you a story about Thurston quest, which I would call Topology implies geometry, that resulted in several fundamental theorems in quite different worlds, namely in the world of geometry of three manifolds, in the world of geometry of surface homomorphisms, and in dynamics of rational maps. So personally, I'm coming actually from the last world, from the world of dynamics of rational maps, but apparently the work of Thurston was, it had quite a lot of ideas that are applicable in all these three setups. And essentially, these ideas arise from the study of technical theory. So the plan for today is actually to discuss with you in some details the three results of Thurston, and also to discuss with you the common technical machinery that is used in his work. So in the first part of the talk, I will mainly just talk about the three results, and the second half of the talk, I will try to go into details, in one of these three results, depending on your interest. So but actually before we start talking about Thurston's results, let's just go to some ancient, mathematics, mathematics of the 19th century probably, which talks about geometrization of two manifolds. So we know that essentially if you have any compact-oriented surface S, then it meets one of the three standard geometries: spherical, Euclidean, and hyperbolic one. And as we all know, the first two are kind of really rare, so there are only finite many cases. But in the third case, the world of the hyperbolic geometry is really vast, and that's sort of the generic case. And the same kind of result is also true if the surface S is assumed to have apertures. So this is a result of this flavor. Topology implies geometry. So if you have some topological surface, you can endow it with some geometrical structure. And except some few cases, this actually geometrical structure is of unique type of hyperbolic, but in fact, within the same type, so for instance, there are infinitely many different conformal structures on torus, as we will see later in the talk. So the type of the geometry is unique, essentially, but there is still some flexibility in terms of the homotopy information, which we'll talk about a bit later. So motivated by this result, we could ask, the same question in the world of three manifolds. So suppose that we are given some topological three manifold. Its result due to Morris that it admits essentially unique piecewise linear and smooth structures. But what about a geometric structure? Where by geometric structure I mean that M should be locally modeled on some homogeneous space. And essentially that was the question that Thurston wanted to answer in the world of three manifolds. And here is essentially his conjecture, his geometrization conjecture, which says that given any closed oriented three manifold, you can canonically decompose it into pieces so that each piece carries one of the 8 standard homogeneous geometries. So there are three cases, and the first three cases are kind of standard ones. Okay, so it's a spherical, Euclidean, and hyperbolic one. So those are natural generalization of the surface ones. But then there are two product structures, and there are also three special ones, which I'm not going to talk about. So what I want to remark maybe about everything except the hyperbolic ones is that one could actually completely classify all manifolds that have these 7 other geometrical structures. So there is a complete topological classification which manifolds can admit these other 7 structures. And again, the world of the hyperbolic manifolds is the generic one. So that's the generic.
But by non-hyperbolic, you mean in the decomposition there is no hyperbolic piece, or?
By non-hyperbolic, I mean that there is a complete classification of pieces that locally look like one of these other 7. So they are they essentially fiber of a circle and related to Seifert manifolds. So we can talk a bit briefly about this later, but for now, what I want to discuss with you without going too much into details of this result. Yes, I should probably first say that this was Thurston's vision, so he anticipated essentially that this should be true. So he crystallized these 8 geometries, and he claimed that these geometries should be enough to locally decompose the manifold into pieces, but he was not able to prove this theorem in this generality. So this result was essentially proven by Perelman. But today we're going to talk about, maybe in the second half of this talk, we're going to talk about what actually Thurston did concerning this geometrization conjecture. But what I want to talk about now about this result is actually how do we decompose 3 manifolds into pieces. And this is done by cutting your manifold along essential spheres and tori. So I'm only going to define right now what is an essential sphere because that's the easiest thing to do. So if I have a sphere that is embedded in the manifold, I call it non-essential if it bounces 3 balls on one of its sides. And otherwise, I call it essential. So now, well, it's a standard thing due to Kaiser and Milner essentially that one could use essential spheres to provide the so-called prime decomposition of S3 manifolds. And then one could use, one could start decomposing this, the remaining pieces even further using essential tori. And this is the so-called JSG decomposition. So what the moral of the story is that the idea of decomposition was old, and Thurston essentially claimed that, well, if you do this kind of decomposition, then you would be left with the pieces that would have locally homogeneous geometry. So that was kind of Thurston's vision about this decomposition. All right, any questions to me about this part? Yes?
Okay, so decomposing the pieces is you give a bunch of open subsets which are disjointed, whose closures are the whole thing. What is a piece, I guess?
Yeah, so what is a piece here? Yeah, so, well, I should have probably said this kind of more completely. So when you have an essential sphere, all right, what you can do, you can cut it out from your manifold, and then you get, well, 1 or 2 pieces, depending on the station, and then you fill in this thing, well, I mean, the complement with the 3 ball. So what you get are like a new 1 manifold or maybe 2 manifolds with simple topology, meaning that you get a smaller fundamental group, okay? And then, you could iterate this process, yes. So the piece is what you get after this decomposition.
Okay, so in being pieces are not subsets.
Yes, pieces are not, well, they are not subsets, yes.
Okay.
So is this clear? Yes, so, I know it's really hard to make some simple examples, but I know you could, imagine having some kind of knot, or yeah, so let's say like this one, yeah, whatever. Yeah, so and then you take a tubular neighborhood, of this knot, and imagine you have 2 copies of this knot. Then you take a sphere around this guy, and this is essential, yeah. And you cut it out, you fill it in by the full ball, well, by the full 3 ball, and then you have 2 pieces with simple geometry, well, with simpler topology. So that's how you should think about it.
Maybe one more question. So in the 2-dimensional case, right? I mean, you essentially have 1 geometry on these things, but then you're looking at things that are, I don't know, like constant curvature or something like this, right? Because I can.
Yes.
And what's the condition in 3 dimensions?
Well, I mean, yes. So we do we ask each piece to carry local homogeneous geometry. and then
Okay.
it's the only homogeneous spaces are these 8 ones that I showed. And that is actually what you want to have. You want to have charts on your manifold, from your charts from your manifold to one of these, 8 model spaces, and the transition maps should be isometry. So that's the structure. Yes.
The inverse of this cutting is taking connected sum, right?
Say again?
So if you want to undo a cut, then so it gives you a way to take connected sums to build your map.
Yes. So that's something that would be relevant later. Yes. So if you want to undo the cuts, then you want to take indeed some connected sums. So let's see, maybe in the second half of the talk we'll actually not talk about decomposition, we'll actually talk about group stuff. Yeah, so that's the 3-dimensional world. But as I said, there are 2 more results, so let's move now to the world of surface automorphisms. In this setup, what do we have? We have a closed-oriented surface S, possibly with finitely many punctures P, and I have an automorphism F on this surface that preserves punctures, all right? And then the Thurston theorem tells that there exists a canonical way to decompose your map into pieces so that each piece is either periodic or pseudonymous. So we're actually going to stay on this theorem a bit more, so I'm going to actually explain this theorem completely. So I'm going to explain carefully how do we actually decompose surface automorphisms, and I'm going to explain you what are these pieces. So right on the next slide, well maybe in 2 slides. But I want to first maybe see that this kind of decomposition is motivated by the case of the torus, which is kind of very easy and can be understood quite explicitly. So if we look, so in all this theory, we look at automorphisms up to isotopy relatively the marked set. If you have just torus, then the corresponding mapping class group is just SL to Z. So what is a mapping class group? So you look at all orientation preserving homeomorphisms, and then you quotient out by the ones that are isotopic to the identity. So you get a group, and in the case of the torus, this is generated, so this is just SL to Z. And now, if you have an element in your mapping class group, then you can associate it some matrix A, and then you could essentially classify different types of automorphisms based on the absolute value of the trace of the corresponding matrix. So in particular, if the trace is either 0 or 1, then the matrix would be periodic, and then we also say that F is periodic. If trace of A is 2, it means that you have double eigenvalue, which means that you have a direction that is being preserved, and this case is called reducible. So you have some closed curve that is being preserved by your homomorphism F. And in the last case, you have, trace of I in the absolute value is greater than 2. So it means that you have 2 eigendirections, like V1 and V2. And what does F do? It stretches one direction by some factor lambda, and it contracts the other direction by the factor lambda. So that's what the situation in this case. So let's say that this is lambda V1 and this is lambda V2. In particular, what you can do in this case, you could look at the foliation of the torus given by the direction V1, and this foliation would be invariant, and it's going to be, contracted by the lambda factor. So I should use 1 over m. And the other direction is being expanded by the lambda factor. So with this in mind, we can actually talk about the decomposition pieces. So there are, as I said, there are exactly 2 types, as I said. So we see that an automorphism is periodic if some iterate of it is isotopic to the identity. So in particular, you could imagine having this surface and just rotating it and then you have period 3. Okay? And well, we say that f is pseudo-analysis if you have two transverse foliations with finitely many singularities such that f is lambda stretch along one foliation and is lambda contraction along the other one. So how you should think about the local picture? Well, you have like some parallelogram given by the two directions, right, of your foliations, and then like contract this parallelogram in one direction and you expand it in the other one. So that's so put it differently, the local picture looks exactly as the one for the analysis of automorphism, except that you're also allowed to have singularities.
Is there any condition of the singularities, or they can be random?
Well, so the singularities are finitely prone singularities. Those are the one. And you have finitely many, of course. So any questions about this too? Yes?
I know technically what a foliation is, but I have zero intuition for them. So could you say a bit more about them? Like, how do they come in?
So you should really imagine maybe about this in the following way. So except at finitely many locations, where you have like this picture that looks like this, where you have a singularity, you have the local picture that is given by the pseudo-analysis structure. So you have essentially a chart which is given by like some parallelogram that like have natural like two directions, and then with respect to these charts, f just like contracts and expands at once. So that's how you should think about it. You could put nice local charts that would respect this structure. And then, as I said, so and then like draw some special parts like where you have key prong singularities. So you have one foliation like doing something like this, and then the other foliation, yes, it's transverse and does like something like that. Well, but again, like if you look at anywhere away from the singularity, you still have this local model given by this analysis space.
Maybe
I
Misha, can
think
you?
like the flows of vector fields outside the singularities, right?
Yeah.
To be a good picture.
And how exactly are you measuring what it even means to stretch or not stretch? I mean, a foliation chart is just a foliation chart, and you're just okay.
Yeah, so it's a measured foliation, like so there exists a measure. Okay, so I'm kind of swiping some things on the rock here, so it's a measured foliation. Yes.
You can also look at the holonomy,
You could also do this, yes.
You can. Oh, okay, I see.
and it's automorphism.
No, but I mean, he was talking about charts, right? So in charts, you don't see anything. Right? But with holonomy, I see.
Yeah, so, all right, yeah, so, okay, I told you what are the pieces, right? But I haven't told you yet how do we decompose our surface automorphism. And we decompose it using invariant multiples. So let's suppose that we have some marked surface. So let's say that this blue guy is our surface and it has, let's say, two marked points. Then, if I look at some simple closed curve gamma in the complement of this marked points, I see that it's non-essential if gamma bounds a disk. So in particular, this green guy here and this green guy here are non-essential. Bounds a disk in S, I should have finished written this out. Yeah, bounds a disk in S with at most one marked point. So I have, yeah, so what's written right now is not actually correct. So if it's bounds a disk in S with at most one marked point. So in particular, these guys are essential. And otherwise gamma is essential, so in particular these two orange guys are essential. Alright? And a multicurve on the surface is a finite set of essential curves that are pairwise disjoint and non-isotopic relative to marked set. So in particular, these two orange curves would form a multicurve. So with this in mind, we can actually define invariant multicurve. So now we need to introduce dynamics. So let's suppose that I have some automorphism. Then I say that the multicurve is F invariant if image of each curve from a multicurve is isotopic to a curve from the family. So in particular, like if you imagine like f that just flips these two sides, then these two curves will form an invariant multicurve. Yes.
Sorry, when you say relative to P, is it allowed to commute P? Or is it allowed to commute P if P fixes the set? Or
So
if P fixes
when I write RLP, I mean isotopy related to point P. So I mean that like
P is a set of points. Are you allowed to commute them?
I'm not allowed to commit them. So each
Okay.
point should be fixed.
But then you can't do that.
Yeah.
You just said reflection, and that would not.
Well. I mean, this guy is allowed to. Automorphism can do, but the isotopy cannot.
Oh, the automorphism can be. Sorry.
Yes.
Okay. Yep. Great. Thank you.
Okay.
Clear.
So isomorphism just preserves the marked points. Okay, so it does not have to fix the pointwise here, but.
But it doesn't even have that problem because f of gamma will be isotopic to f of gamma, right?
F of gamma should be isotopic to some curve.
Yeah, but is this example it will be?
Yes, it's isotopic to some other curve. Yeah, this is perfectly fine. And this is actually something you should expect. Yes, so like that, like curves are being permuted in some way. So actually, well, let me say this maybe already right now that we have a finite collection of curves and we have an automorphism. And well, by this condition, like it actually means that if we have an invariant multicurve, then f permutes the curves. So f acts as a permutation on the curves. All right. But we could actually say something more, as we will see that like if you look at the complement of the multicurve, then f would act as a permutation of the corresponding pieces. But before I go into there, let me just mention already one definition right now. So I would say that the automorphism of f is reducible if it has an invariant multicurve. Okay, so.
But if this happens, can't you start moving the curves up to isotopy so that they really become invariant? They are taken one into
Yes,
the other?
yes. So like, I mean, in all these constructions, we are considering maps up to isotopy. So if you have an invariant curve, then you could change your f up to isotopy so that it actually fixes this set of curves.
Oh, you're going to change f because I was
Yeah.
suggesting to change gamma by isotopies so that it becomes truly invariant under f. So that
Let's do it other way around because we actually, in all the results that I will be seeing, we do not actually say something about the map f itself. We say about the map within the same isotopy class, within the isotopy class. Okay, probably okay, you might be right that like you could do it the other way around, but like in this direction it's much easier to see, and in a sense that's not so crucial. Yeah, but what I already like started to see that like if we have some invariant multicurve, what we can do like we can just take like pair of scissors and cut our manifold along this invariant multicurve, and then due to the invariance property, what would f do? F would just permute the pieces. So in particular, like if you consider this map f that flips these two guys, then in the middle, so the middle piece would be just fixed by f, and these other two pieces would be permuted by f. So know that like each piece that I consider gets a new marked point. So how you should think about this, like you cut your surface up and then you pinch, like this curve to a point, and then you have an extra marked point in orange. Or you could also say that like you glue in a disk with an extra marked point. Whatever you prefer. But the crucial thing, like is that because it's a permutation, it means that like you can look at the first return map to each piece, and this map is well defined up to isotopy. So on each piece you get an automorphism given by some iterative map. So now with all these definitions, we can actually completely understand certain
But
instances.
some may switch the markings, right?
Yes.
Not preserved, like, okay.
So you, yeah. So each automorphism can be canonically decomposed along some invariant multicurve, which is actually maximal one in the pieces, such that for each first return map, it's either periodic or it's isotopic to epsilon. So that's the complete statement of the Nielsen Thurston decomposition.
sorry, in your original slide where you defined the pieces, there were 3 different pieces. Can you remind me?
Yeah, so I have 3 different pieces.
Yes.
Yes, and on each piece, I may consider the corresponding first return map, and the corresponding first return map is one of these 2 types.
Okay, but I'm sorry. In your in the original thing, you said something about like, okay, I either have I can call something periodic or pseudo. Or there was
Yeah,
a third
so,
one. What was the
okay,
third
I see the
one?
question, yeah, so in the original thing,
My point. Here,
so in the case of the torus, right,
No.
which is our motivation, so if I have torus, then we have
Oh,
three
the
cases.
reducible ones.
Exactly, periodic, pseudo-anosa, and reducible. So if you have an invariant multi-curve, you are automatically in this reducible situation. And if you don't have any invariant multi-curve, then you are in one of these. Okay? Yes?
And this, so that each first return map,
Yes?
that means as much as you need to make sure that it maps, say, a particular disjoint union to itself, or what does it mean? Because now, for example, if you look at the map over there, it maps 2 components to one another. Like there's not.
Yeah, so the map maps this guy up here and this guy up here. But
Yeah.
I can consider the second iterate. And what would it do? It would map this guy up here and then bring it back.
After
So I-
the connecting component, we take the highest power.
Exactly.
Yeah.
So
The
F acts as permutation on components. So therefore,
Yeah.
you could find some power. Well, in fact, you could find some common power that would fix everything.
Misha, what comment did you make about reducible again? Sorry.
Yeah. So there was a question, like why I have only 2 cases here, even though like for torus I had 3 cases: periodic, pseudo-anosa, and reducible. Well, and also. And the answer is, of course, is that well, if I have an invariant multi-curve, then automatically in the reducible situation. So that's what was our definition of a reducible curve, is that if it has an invariant multi-curve. And then, if there exists some nice, invariant multi-curve with respect to which, I can decompose so that, each other piece will not have, each other piece is either periodic or admits this pseudo-anosa structure. So that's necessary. So are we good? Okay, so that's a theorem from the world of surface homeomorphisms.
But isn't that clear? I mean, how difficult is it to prove in all detail?
We can actually prove it. Yeah, so if you want, I can prove it in the second part of the talk. Well, model some videos, but I can prove it.
My question whether it's doable right away. But I think
No, it's not. Well, okay,
But
if
it
you-
doesn't take Perelman to prove it. Right?
These days, no.
Okay.
But at the time, you have to come up with the right story. You have to come up with the right way to look at the things. And I'm not telling this only, but in fact, Thurston's result actually proves something stronger. We could also discuss later. But okay, let me just put it this way. So I'll prove some version of this result in the second half of the talk, or maybe well, let's see. But for now, I want to talk about the third world, and this is the world of the rational maps, where, so to say, I live. And in this world, what is essentially the main contribution of Thurston, that he had this idea that you should really abstract from the rigid structure of complex Riemann sphere that you are looking at, and consider some more flexible situations which are branch covers. So if you have a rational map on the Riemann sphere, then it's clearly a branch covering map. So what I mean by this, it's continuous, surjective, and locally acts as a power map. And what Thurston was asking, so he was asking the following question: suppose that you have some branch covering map on the sphere. Can you realize it by some rational map? Here, there exists a specific notion of realizability, which I might define later in the talk, but for now, you should just think that F and G are conjugate up to isotopy. So conjugation is too strong to ask, you again need this flexibility up to isotopy. So maybe let me still draw this diagram. So you have, let's say a map, your branch covering G, and I want to have some rational map F, and I want to have like the following diagram where H and H prime are not the same, but they are isotope. So I want to have a conjugacy after some natural isotope. So that's what we are. And well, so Thurston answered this question in his famous result, and one need to be more precise about the setup. So what is the setup that we are looking at? We are looking at the setup of the so-called post-critically finite branch covers. So what do I mean by that? So I have a branch covering map G on a sphere with marked points, so it should preserve these marked points, meaning that like G maps marked points to marked points. But not only that, so I ask the set P to be finite, and I also ask the set P to contain all the images of critical points. So if I have a branch covering map, right, my map is locally injective except at finitely many points, which are called critical. And I want my set P to include all the images of these critical points. Okay? And in particular, like thanks to this condition that G of P is a subset of P, automatically each critical point has finite orbit. So if I have a critical point, I know that its image is within P, but then G of P is a subset of P and P is finite, so therefore each critical point has a finite orbit. In particular, it means that it's either periodic or pre-periodic. So that's the setup that Thurston was looking at. And now what is the decomposition result in this case? Suppose that you have some post-critically finite branch cover, then again you can find some canonical nullity curve gamma decomposing F into pieces of three types, namely homeomorphisms, quotients of torus endomorphisms, and rational maps. So again, similarly to the previous result about surface automorphisms, we have some natural decomposition into canonical pieces. What are the canonical pieces here? The homeomorphisms, quotients of torus endomorphisms, and well, the most natural thing from the point of view of rational dynamics, rational maps. So that's the result of this piece. Yes?
What does quotients of torus endomorphisms mean? Because if you cut, you cannot make a torus out of it, right? So
Yes. You have the following situation. So you have a torus, you have an endomorphism of the torus, and then you have some projection on the sphere, so some branch covering. And then this is this is quotient of A. That's all. So what's the most, classical examples to consider? They are the so-called lattice maps. So, imagine that you have two Euclidean squares, you glue them together along the boundary. You could naturally view it as a Riemann surface. So you could uniformize this guy, and this is going to be a Riemann surface. And then what you do, you cut each square into 4 pieces and color them in the checkerboard manner, and you define a map. Let's say that would map the white pieces, let's say, to the front face of your original square, and the black pieces to the back side of the sphere. And this gives you actually some rational map. And you could view this map as a quotient of z goes to 2z for the vectors.
So, did you mean to say rational map? Or
Yeah, so this map is actually rational.
Okay, but also according to the torus.
It's yeah, so there are some exceptional cases which might or may not be rational, yes, that are determined by these quotients of torus homomorphisms. Yeah, so I should say that, yeah, in this version, this result, is really due to, not just Thurston, but also including a Salvi, who kind of formulated the Thurston result in this way with some extra work. Yes. So again, if time permits, we can talk about this decomposition a bit more, but I want to move to the machinery. So I promised you to talk about the common machinery. This played a crucial role in all the three results, in the work of Thurston in these three different worlds. The common machinery is Topology theory. So the Topology theory studies different possible complex structures that you can put on a surface. So what do I mean by this exactly? So suppose that I have SP some marked closed oriented surface, and then I can form a structure on the surface is a pair x phi, where x is a Riemann surface and phi is some homomorphism from the given surface to the Riemann surface. So a conformal structure is a pair, Riemann surface and the corresponding marking. So this map phi is usually called the marking. And then you can define natural equivalence relation of the space of all conformal structures. So you see that two conformal structures are equivalent. So I have two conformal structures given by phi and phi prime, and I say that they're equivalent if I have some biholomorphic map I, so that this diagram commutes up to isotropy. So what does this mean? It means that the decomposition of f and I is isotopic to phi prime. So that's the equivalence relation. And what you look at the space of all conformal structures modulo this isotopy, and you call it the type space. All right? So know that this guy is stronger than, just is larger than just remembering just conformal structures. We also remember the corresponding homomorphism. So which means that we also remember some isotopy information about the way we put the conformal structure on the surface. So in particular, if we just look at the example of the torus, then the type space of the torus is given by the hyperbolic plane. So let's say that H2, let's say that it's the upper half plane model, then you can describe different conformal structures on torus just by some number tau in the upper half plane, which tells you which parallelogram you should take to glue the torus. So you take the parallelogram with given by two vectors which are 1 and tau, and then you glue the corresponding torus by identifying the opposite sides, and you get all possible different conformal structures on the torus. All right. So one quick remark that, as I said, what's important is homomorphism, because even though this guy and this guy they define you two isometric Riemann surfaces, well, the homotopy type is different. So essentially, this guy gives you, let's say, so this guy essentially gives you the canonical way, so to say, and this guy is a twist. So you have the same Riemann structure, but the embedding, but the marking homomorphism is given by the twist of the first one.
In this discussion, you use topological and homeomorphism. Can't you replace them by smooth?
Yeah, so
Does it make?
No, I mean this makes perfect sense here. So like and actually that's maybe much more powerful way actually to do things. Is like instead of like talking about automorphisms, you talk about smooth automorphisms. Okay, so like well, except maybe like with some funny points here. So you could always like replace, let's say, homomorphisms by smooth guys, and I don't know, again, like by the result of Modular, like you could, let's say, replace topological manifold by smooth manifold, by smooth manifolds. Yeah. So this is important if you want to really actually do things carefully. Yes. So what can we see about this Teichmüller space? Well, it has some natural topology, and the simplest way to describe this topology is given by the Lang's function. So what is the Lang's function? You look at the space of all isotopy classes of simple closed curves on your surface S. Then you look, so suppose that like you have some point time in your Teichmüller space, meaning that like you have a Riemann surface X and a marking phi. So if you have some curve gamma, what you can look at, you could look at that. So this should be phi gamma. So you can look at the image phi of gamma on the surface, on your Riemann surface. And then with this isotopy type, you have a geodesic, and you take the length of this shortest curve. And this is how you define this map. And you could use this length function to define, so this length function is injective, and it defines some natural topology of the Teichmüller space. So you look at the corresponding Riemann surface, and you look at the lengths of the shortest geodesics within all possible isotope types. But in fact, one can show that Teichmüller space is simply connected, and in fact it's isomorphic well to the following power of R. And let me also tell you like how you should think about this. So one can actually show that if you have a pair of planes, then the conformal structures of the pair of planes are described by the lengths of the corresponding boundary curves. So the Teichmüller space of this guy is isomorphic to the third power of R plus, where each component gives you the length of the corresponding boundary curve. And now if you have an arbitrary surface, what you can do, like you can cut it into a pair of points, and then if you just do the computation, then you will have exactly 3g minus 3 plus number of punctures curves. And then you have, I should have, again, like sorry for the typos. Yeah, so you have R plus to this power, which corresponds to the length of the curves. And then you also have the twist parameters. So when you have, like two pair of planes and you want to glue them together on the boundary, well, you may also twist. And this would define different control structure. And the twist is a real parameter. So that's why you have this R to this power, which, so to say, corresponds to the twist, and this corresponds to the length of the curves, and these are the so-called vector Nielsen coordinates on the Teichmüller space. But again, like one can do something more than that, and actually show that, like Teichmüller space some analytic, complex analytic structure of the appropriate dimension.
Wait, sorry, I'm getting a bit lost. So this Teichmüller space, it consists of equivalence classes with conformal structures?
Yes.
Right? And these conformal structures, they give you, what do they do again? They give you a way to glue your manifold.
Yeah, so how can you essentially describe a conformal structure on manifold of some large genus? You cut it into pairs of pairs, and then like you put some conformal structure on each pair of pairs. Of course, if you want to glue these guys, then the lengths of the curve should be the same, right? But then when you glue things up, you could actually twist. And if you glue things up, maybe with some twist, this would define you a conformal structure on the whole manifold.
Right, so that's how you get from the diagonal space of pairs of bands
Yes.
to... yeah.
Yes, yes. Or what was the question? Yes.
Well, more just actually definitional even, like how, what these conformal structures are and what is the point, like why are we interested in these things?
So the point is that we want to, well, I mean, that's not at all clear maybe right now how this is related to the previous three results. Well, except maybe, you know, like in the rational case, okay, maybe let me tell you why it's relevant in the rational case, and in a sense, the very similar kind of story is in general. So look, this H up here is a homomorphism from S2 to the Riemann sphere. So it's an element of the Teichmüller space. Okay? So now, let's suppose that I start with some homomorphism, H. Okay? Then what I can do, I can take the standard complex structure on the Riemann surface, I can pull it back to S2, then I can pull back this complex structure by the branch covering map G, get a Riemann structure on S2, and then uniformize it together. And uniformization corresponds to the fact that I'm having some new map H prime. So I have some new point in the vector space. So now if I want this guy to represent a rational map, I essentially want this H prime and H to be the same point as the vector space. So I want this H and this guy to be isotopic. So this isotopic condition, you know, like, is a very natural thing if you want to think about invariant complex structures where you allow isotopes.
Can one say that the conformal structure is just a geometric structure? Therefore, it's very interesting.
Well, it's more than just, you know, like the geometric.
Under the appropriate notion of equivalence, like you look at the space of splitting structures or
Just, yes, yeah, so in the sense that
it's like you look at space of interesting geometric structures. In this
Yeah.
case, it's conformal structure. It's close to Riemannian.
yeah, so well, I mean, there is like one subtlety that, you know, like from my perspective, the different kind of geometry, like the different like Riemann surface structure, is more like the modular space structure. And here we are worried not just, you know, like about, I mean, about what is the Riemann structure up here, but also worry about like how do we actually put it there? What is the homotopy information of the corresponding coordinates? Yeah, so that's actually then I think, yes. So there is another natural space which is called the modular space of a surface, and this is the space of different Riemann surface homomorphic to the given one, up to, you know, the conformal isomorphism. And then actually the Teichmüller space is the universal covering of the modular space, and the corresponding group of diagonal summation is exactly the mapping class group. So if you look at different possible, you know, like Riemann surfaces X, then this gives you the modular space, and the Teichmüller space also records the homotopy information, and then it becomes the universal covering of the modular space with the diagonal summation given by the, like all the possible ways, you know, like how you could twist your manifold, which is exactly the mapping class. And yes, question?
What was P again? Sorry, this is the meaning of the symbol.
P?
P. Like it's the
P is, yeah, so this I here, yeah?
Yeah.
Yeah,
Yeah,
so,
it's the Teichmüller of S, comma P. But what P
so,
is?
so P, so you have a surface with finite set of markers.
Oh, the markers.
Yeah, so P is a finite set of markers. And pi is, well, the natural covering, so if you have, you know, a pair Riemann surface of pi, then of course, like, you have all this projection on the first coordinate. So that's how it's defined.
Also, Misha, so you wrote that pi is a universal covering, but I mean pi has some isotropy and so on, right? There's like singular.
No.
No, so it's really like
Yes, and maybe also like a quick remark, which would be relevant maybe in the second half of this talk. if I have, like an element of the mapping class group, then I could define a natural action on the tactile space by just pre-composition. So if I have a point x phi, which means that like I have a homomorphism from S to S, then I can just pre-compose it with the mapping class group element and get the natural action. So it's going to be the left action if I compose with F, or if you want, sorry, the right action. And if you want to be a left action, then you should compose with F inverse. That's my tough choice. All right. How much time do I have? Let's see.
Maybe you could have a break in 5 minutes or so. I don't
Yes,
know if that
yeah,
five
yeah.
or
So
five
that's
or 10
what I'm
minutes.
shooting for. I'm just trying to think like how I should wrap this up in 5 minutes. Okay, let me still like do one more thing, or maybe not, but depending on how people are familiar with quasi-conformal maps. No, okay. Let me just jump up here straight, okay, and we could discuss the details later. So, yeah, so something I haven't said, that there exists a natural metric of the tactile space, and this is defined using quasi-conformal homomorphisms. We will talk about this later, but for now, let's suppose that you have some natural metric D, okay? And let's suppose that I have some automorphism F. And what I'm after, like I'm after this classification of different possible types of surface homomorphisms. Remember, we had like this periodic, pseudonosive, and reducible. And the crucial idea that you can actually distinguish these three different types of homomorphisms just by looking at some very special quantity, which I denoted by delta F, and is defined like this. So suppose that I have some point in the tactile space tau. As I just said, there exists a natural action of the mapping class group on tau. So I can look at the image, which I would denote by sigma F of tau. So it's the image of tau in the mapping class group action. And then what I could do, I can look at the translation length. So I can look at the distance between tau and its image, and I look at the infimum of over all possible starting points. So this is the translation length of sigma F. And then, essentially, depending on whether this infimum is realized or not, I could do the corresponding distinction. So if infimum is realized and is equal to 0, then the corresponding guy would be periodic. If infimum is realized and positive, then the corresponding guy will be pseudonosive. If infimum is not realized, doesn't matter what it is, 0 or positive, then F would be reducible, meaning that there would be some invariant multiplier. So this translation length provides you a way to distinguish these different types of automorphisms. In particular, what you can do, like you can just essentially look at the translation length, and if it's not realized, then you automatically get some invariant multi-curve that cuts your space into the pieces. And then you, well, in principle, you might need to iterate it, so you have the corresponding pieces. Potentially, you might still want to apply this thing, but actually you don't need to. And then the pieces will become periodic or pseudonosive.
But if it's not realized, the infimum is not realized, you'll have a few limit points. And you take this curve and you split it into parts. Will the parts realize those limit points? I know you see what I mean.
Yeah, I'm not so sure.
So you're taking infimum over distance.
Yes.
You say it's not realized.
Yes.
So that means that that sequence of distances can converge to a couple of different numbers.
No, it means, well, okay, so I should correct myself. Infimum is realized, I mean that there exists some specific point tau that delivers the infimum. That's what I mean.
Oh.
The infimum is a unique
I see,
thing,
I see,
right?
I see. Yeah.
But the question is whether there exists some special point tau that delivers this quantity. And depending on whether this point exists or not, you distinguish the stations. Yes, okay, maybe let me just jump to this slide and then I stop and we could have a break. Yeah, so essentially I should say that, in all three worlds that we discussed, in the world of rational maps, in the world of surface homomorphisms, and also in the hyperbolic world of two manifolds, Thurston introduced some natural map on some relevant active space sigma, and then the question whether your situation can be geometrized or not is related to some fixed point argument for some map sigma on the diagonal space. So in all these three different worlds, there exists a common machinery given by the diagonal space, which nicely embeds in the story. So in particular, that's something that we could also discuss in the second part of the talk. In the world of three manifolds, sigma is related to the so-called scheme map that Thurston introduced. Yes, so maybe that's a good place to stop the first part of the talk.
Okay, thank you.